Hi everybody, welcome to lesson 7.6 where we will be exploring exponential functions. Our goal is to be able to write, graph, and recognize an exponential function. Find the place in your notes where you will be writing the exponential function. This is what it looks like. Y equals a times b to the power of x. The a represents the y-intercept. This is the place where the function is going to be touching the y-axis or passing through the y-axis. It's the point when x equals 0. The b is the constant factor of change. So that's what's being multiplied. So you see the dot here. So the b is what's being multiplied, that constant factor of change. If you need to pause the video to go ahead and write this down, please do that and then you can continue. All right, we're going to do a little exploration. I have two exponential functions, this one and this one. Notice that for both of them, the a value is exactly the same. And remember, that is the y-intercept. That's the place where this function is going to touch or pass through the y-axis. What's different is the b value, which is the multiplier. So we can see here in the first one, we're multiplying by 2, and in the second one, we're multiplying by half. So we're going to explore what do these two exponential functions look like if we graph them on a coordinate plane, and what do the numbers in the function actually tell us. Okay, so let's start off with the one on the left. So what we're going to do is come up with some points that are going to help us graph this function. So we're going to start off by just plugging in 0 for x into the function. So I'm just going to make the x a 0, and then we're going to evaluate for what y is. Y equals, this would be 10 times, and 2 to the 0 power is 1. So y would be 10. Now this should make sense because I told you that the 10 here is the y-intercept. It's the point when x is 0, so 0, 10. So if I were to graph that, it's going to be right on the y-axis. Okay, we're just going to erase what we just did here because we're going to plug in another value. All right, so now we're going to go back to the table. Let's plug in 1. So plugging in 1, 2 to the first power is 2. And when I multiply, y equals 20. So go to the graph, over 1 up 20, and just make a point there. And then we're just going to plug in the next value, and you should kind of notice a pattern here. So if we plug in 2 for x, 2 to the second power is 4, and 10 times 4 is 40. And then we're just going to go right over here, over 2 up 40. Okay, we'll do one more. Okay, plugging in 3, 2 to the third power is 8, and 8 times 10 is 80. Okay, so over 3 all the way up 80, I'm kind of getting off my graph. I'm going to be getting off my graph after that. Now, what I want you to notice is there's a pattern in the y. Look at the y values in the table. Do you see the pattern happening here? Times 2, times 2, times 2, it's doubling. That's our multiplier right here. That's our b value. That's our constant factor of change. We're doubling. So it's safe to say that when I plug in 4, it's going to be 160, and I'm going to be off my graph. So let's connect the points. Do this with me. We're going to connect the points. We're going to see this nice exponential curve, this growth here. See how it starts off small, but then it really flies, right? It really curves up, and we see a lot of growth. Now, quickly, I just want to connect this to what you guys know with linear function. So if this were linear and I draw a line, remember linear is perfectly straight, constant rate of change, right? So do you see how with linear we have that constant growth? With exponential, we start off slow, kind of like linear here, but then we really grow quickly. Okay, so that's the difference here with the exponential versus what you guys are familiar with linear. Okay. All right, so now we're going to go over to the other function and on the right here, and let's go ahead and graph this one and see what we notice. All right, so I'm going to start off by plugging in 0. And we're going to get y equals 10 times, and 1/2 to the 0 power is just 1. So again, we're going to see that we have the same y-intercept, 0 all the way up here at 10, you guys. Way up there, we're going to make the point. I number this just a little bit differently. Okay, so that's the first one. Let's erase. All right, so plugging in 1. half to the first power is 1/2, and half times 10 or half of 10 is 5. So over 1 up 5 would be about here. Let's go ahead and we're going to plug in 2. Now 1/2 to the second power is 1/2 times 1/2, which is a fourth. So now we want a fourth times 10 or a fourth of 10, and that's going to be 2.5. So going over 2 up about 2.5, which is about halfway. About here. Okay. Now I want to see if you notice something. Let's get rid of this. There's also a pattern in the y. You see what's happening? We're taking half of, half of, half of. Half of 10 is 5. Half of 5 is 2.5. The multiplier is 1/2. The constant factor of change is multiplying by half. And that's the pattern we're going to see. 10 times half is 5. 5 times half is 2.5. Let's continue. If I take 2.5 and I multiply it by half of that would be 1.25. And let's graph that over 3 up about 1.25. And then if I multiply by half again, I would get 0.625, which is a little bit more than half of a unit. So over 4 up about here. And then let's go ahead and just connect our points. We're going to see this nice decay curve, exponential decay. Now it gets really, really, really close to 0. It never actually touches 0. But we see that if you look at the very top, right up here, you fall very quickly and then slowly, slowly, slowly as the line comes down. So this is an example of exponential decay. So let's just kind of review here what we're noticing. Okay, in both of these, we have the same y-intercept. They're both 10. We can see that on the graph, the y-axis, the lines across the 10. But what I want you to notice here is the b value, the times 2 and times 1/2. Just by looking at that first one, that times 2, that tells us that that's exponential growth because the multiplier, the b value, is greater than 1. Okay, this is bigger than 1 right here. And over here on the right-hand side, this is exponential decay because the multiplier is smaller than 1. And so just by looking at that b value in any equation, if it's bigger than 1, it's growth. If it's smaller than 1, it's going to be decay. And that's what we're going to see happening today as we go through our examples. Okay, so now that we've explored the exponential growth and decay functions, let's go into some examples where we're going to be graphing and writing, all right? So number 1, we have an exponential function. We're going to graph it. We're going to decide if it's growth or decay, see what it looks like on the coordinate plane. So just like what we did before, we're going to be building a table of some ordered pairs that are going to help us connect and make our graph. So I'm going to plug in 0 right up here for x, and we know any number to the 0 power is 1, and then I'm going to multiply that by 0.25. So I'm going to kind of think of this 0.25 as money. That might help us, like it's 25 cents, right? Multiply by 1, we get 0.25, which makes sense. This is the y-intercept because remember the y-intercept is this number right here, the a value. That's the y-intercept. So go down to your table or to your graph, sorry, and we're going to go 0, and we're going to go up to about 0.25, which would be right, probably, oops, I got to grab my pen. Right about there. It's just an estimate. It's not perfect. Okay. So let's go ahead and plug in another value. We're going to plug in 1. So if I plug in 1, 3 to the first power is 3, and now 3 times 0.25 or 3 times 25 cents would be 75 cents. So go to your graph, over 1, up about 0.75. It's really hard because these are 2 is the first tick mark. So we're just doing our best here. Doing our best, pretty small. All right, so I'm going to plug in 2 now. 3 to the second power is 9. You might need a calculator, 9 times 0.25, or if you have 9 quarters, that is going to give you $2.25, so 2.25. Okay, so over 2, up about 2.25 is about right here. Okay, enough of plugging numbers in now. Remember that eraser, trying to get my eraser to work, you guys. Okay, remember that this is This b value here, this is the factor of change, the multiplier, times 3. So what's going to happen in the function is we're going to go triple, 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 times 3, times 3, times 3. So I don't need to sit and plug every single x value into the function. I just know this is going to triple because of the 3 and the b. So I'm just going to triple this $2.25 or 2.25. And if I triple that, I'm going to get 6.75. And then if I triple that again, I'm going to get 20.25. Whoop. Okay, let's go graph that. 3, 6.75. So over 3 up about 6.75. And then over 4 up about 20.25, which is way up here. So now let's graph. So you see how very, very slow growth, but then very, very quick. Triple, 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 and we're growing very quickly. So here we have an example of exponential growth. Why? Because the b value up here is bigger than 1. So just by looking at that, I can tell this is going to be growth. All right, next example. Number 2. Now, just by looking at this function, can you tell, is this going to be growth or is this going to be decay? Can you also tell what the y-intercept is going to be? Yeah, I bet you can. So just by knowing that this is the y-intercept, I know that that's the value when x is 0, 18, right? Because if I made x 0, anything to the 0 power is 1, and that whole 2/3 is going to turn into 1. So now let's just go right down. We know what the pattern is going to be. The pattern is going to be multiplying by 2/3. So I'm just going to multiply by 2/3, whether I use my calculator or my brain, and that's going to build me this pattern in the dependent variable. So if I take 18 and I want 2/3 times 18, or 2/3 of 18, that's 12. 2/3 of 12, that's 8. 2/3 of 8, that's 5.3 repeating. 2/3 of 5.3 repeating, that's 3.5 repeating. Or maybe you even put this as a fraction. You could do that. I'm just decimals because it's a little bit easier to graph. Okay, so now we've built ourselves a table. Let's go over and graph it. So 0, 18, y-intercept all the way up here. Then over 1, up about 12. Over 2, up about 8. Over 3, approximate up about 5.3 repeating. And then over 4 on the x and up about 3.5. Okay, now if you graph your points, let's connect them. We're going to see that we are falling, 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 falling. This is exponential decay. Now it looks like it gets really close to the 0, but it never actually touches it. Okay, so that nice curve line there. So yes, exponential decay. Why? Because the b value is smaller than 1. So just by looking at the function, I know it's going to be decay, and you probably knew that too. Okay, so let's just kind of recap. How can you just look at an exponential function, like this one right here, and tell if it's going to be growth or decay? So let's put some numbers in there and see. Okay, exponential growth. If we look at these two that we were practicing with, that we were graphing, how can you just look at these and know that it's going to be exponential growth? Well, hopefully you can answer that question. And because the b value in both of them is bigger than 1, so right here and right here, they're both bigger than 1, that tells us it's going to be exponential growth. All right, these are the decay examples we did. So again, how can I tell it's decay just by looking at it? Well, the b value is going to be less than 1. So I look at the multiplier and I'm multiplying by a number less than 1. That's going to give us decay. So just kind of putting these up here so that you guys can see the difference between the two. We want to be able to look at a function and just know. Okay, example number 3. We're going to be labeling each table as either linear or exponential, and then we're going to write a function rule for both tables. So I'm going to kind of pull back the linear function rule back from chapters 4 and 5 to what we're seeing now with exponential. So let's take a look at the pattern that we see in the dependent variable. So I'm focusing on y. I can see that x goes up by 1, right? Let's look at y. To get from 2 to 6, that's adding 4. To get from 6 to 10, that's adding 4. Does this look familiar? To get from 10 to 14, that's adding 4. When you have a constant adding pattern, that's linear. So we're going to see this is a linear. This is going to make a line if you were to graph it. We see a linear relationship, so let's write a function rule. Do you remember when you were writing function rules for a linear equation? Oop, I got to get the pen. Remember we put y equals box x plus box, right? Remember that? Okay, now I'm going to make you think. Now this first one right here, this first box, that's our slope. That's our rate of change. We see that we're going up 4 on the y and up 1 on the x. Remember, that's your y over x, your change in y over change in x, your slope. So that would be 4. And then the second number that we're adding or subtracting, that is our y-intercept. Remember, that's the b, the y-intercept, and that's positive 2 when x is 0. So the function rule for this table would be y equals 4 times x plus 2. We'll try it. Take this 3 right here, this x value. If I multiply it by 4 in the rule, I get 12. And then do you see how if I add 2, I'll get across the table to give me 14. So that's linear. All right, over here, we can see the x is going up by 1. Let's look at the y. What's happening in the y? Do you see it? It's multiplying by 3. Yes, we're seeing tripling. We see a multiplier. That's exponential. So when I write an exponential function, I have a times b. Oh, I don't know what that was. b to the power of x. Okay, the a, that is our y-intercept. So that's going to be when x is 0. So that's negative 1. And then the multiplier, that's our factor of change, times 3, times 3, times 3. It's tripling, so the 3 would go right here. And there's our exponential function rule, y equals a times b to the power of x. Just to make that a little bit prettier here. Negative 1, there we go. There we go, negative 1 times 3 to the power of x. Okay, so we see both. With linear, we're going to see that adding or subtracting pattern, and with exponential, we're going to see a multiplicative pattern. All right. Next example, number 4. Here I want you to write the exponential function for each table. So I'm telling you that each table is an exponential function. So y equals a times b to the power of x. So you're going to see either multiplication or division patterns in the y. I would suggest maybe just first writing down like a blank equation, y equals, here's your a times b to the power of x, and then plug the numbers in once you start to look at each table. So maybe you want to pause the video and just write that part down, and then we can start filling in everything together. Okay, you ready? So let's go ahead and we're going to start at the top left. So I'm going to look at the y, and I want to look for that factor of change. What are we multiplying by? So 2 times 14, or sorry, 2 times 7 is 14. 14 times 7 is 98, times 7 times 7 times 7. So that's my multiplier. So remember, this is what we're multiplying by right here, times 7. That's where that factor of change goes. But the first number, that's my y-intercept. When x equals 0, y is 2. So this would be my function rule for the first table. For fun here, guys, we're just going to switch up the color. Okay, so let's look at the one directly across from it. So looking for the pattern. Okay, maybe you're seeing it. I'm going to circle when x is 0. That's the y-intercept. So y-intercept is 64. That's my a value. And then I'm going to multiply that by what? So what am I multiplying by every time as I move along my pattern? 64, 32, 16. Do you see how it's taking it in half? It's dividing by 2. But this needs to be a multiply. It can't be divide, because see the dot right here? That's multiply. So when I'm dividing by 2, it's multiplying half. Multiplying by half is the same as dividing by 2. So then this would be a half. That's my factor of change. All right, we're going with purple now. Love purple. Okay, bottom left. Here's your y-intercept. That's 5. So I'm going to go right ahead and put the 5. That's my starting value. Then I'm going to look at the pattern. What's happening? 5 is doing what? 15, 45, 135. Do you see how it's tripling? Multiplying by 3. So my multiplier is 3. I start with 5 and I triple, 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 triple. Kind of getting the pattern here? So much fun. Okay, this one. Last one here. We've got our y-intercept is 7. And then let's see, what are we multiplying by? What's happening? 14, 28, 56. We're doubling. Double, double, double is a times 2. So that's where the 2 goes. The 2 is the b. Okay. Oh, that looks like so much fun. I love the colors. All right. Okay. Now we're going to go back to the McDonald's penny a day scenario. So if you watched that video first on if you were to get paid a penny and then every day that penny doubled for the entire month. So let's write the exponential function for this because this growth is exponential. You're double, 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 right? So let's see if we can write a function rule for that situation at McDonald's. So in order to write a function rule, it makes it really easy if you start with a table. So I'm just going to go ahead and I'm going to plug some numbers in there. There's my 0, 1, 2, 3, 4. And think on day 1, you would be paid 1 penny. On day 2, it doubles. You're paid 2 pennies. On day 3, it doubles. You're given 4 pennies. On day 4, it doubles again. You're given 8 pennies. And this, right, it happens for the whole month. So let's see if we can write an exponential function for this scenario. So here's A times B to the power of X. Okay. I need my y-intercept, and that's when X is 0. So do you see the pattern? Obviously here with the McDonald's penny a day, we're doubling. The pattern is to double. So that means to get back up, I'd have to divide by 2, divide by 2, divide by 2. So if I take 1 and divide it by 2, this would be half. And then go backwards. Half, if I double it, I get 1. Double, double, double. So my y-intercept is half, and then what my multiplier is 2. And so this function right here that you're looking at, that is the exponential function that describes the McDonald's penny a day scenario. Pretty sweet, huh? Yes, I know you think so. All right, let's try our last one, number 6. This is something you're probably familiar with, the ice bucket challenge, starting with one person completing the challenge. That's where it all started. And then they challenged 3 friends to do the same thing every single day. And it grew exponentially because this whole ice bucket challenge is actually an example of exponential growth. And so what we're going to do is figure out the function rule for it. So we'll start with a table because, like I said, it's always easiest to write an exponential function if you have a table. Organize our information here in a table. So when this ice bucket challenge started with one person, I'm going to just change colors here. On day 1, one person did the challenge. And then they challenged 3 other people to do it. So on day 2, when this whole thing started, there was, 3 people that did it. Now, those 3 people each challenged 3 people, and then there was 9 people doing it. Those 9 people each challenged 3 people, and now on the next day, you got 27. And this thing just grew. It blew up because it's growing at an exponential rate. So let's write the function rule for it. Y equals A times B to the power of X. Okay, so I got to go back up to 0. And you guys see triple, 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 triple. My factor of change is tripling. And so I got to undo that by dividing by 3. If you divide by 3, you go back up in the table. So if I take 1 and divide it by 3, it'd be 1 divided by 3, 1/3. And then you see how you triple that, and that would work. Okay, so 1/3 is the y-intercept, and then the multiplier is 3. And so this is the function rule that describes the ice bucket challenge. Isn't math cool? I think so too. There we have it. So just in summary, this was the exponential function. And if you didn't get a chance to fill all this in the top of your notes, you want to be sure that you pause the video now and do that. Our A is our y-intercept when x is 0, and our B is our constant factor of change. We learned that if the B is bigger than 1, it's exponential growth. And if the B is smaller than 1, it's going to be the decay. Thank you for joining me, everybody, and have a great day.